Alrighty. We got started a couple minutes late today, but we were handing out exams. So, again, as I said on the recording, I thought that the class as a whole just did fantastic on the exam. I was just tickled across the board. Seriously, I mean, I thought you did great. If anything, it makes me think I got to make the exam harder, you know, in future. And you're like, listen, hold on before you start getting crazy, you know, with those types of statements. But in all seriousness, I mean, one of the things I said at the beginning of this class is I don't really think that you know, this class is among the most difficult ones that you take. You know, there's not a lot of memorization. The problems are, I mean, they're pretty clear in terms of their output. So again, I think you did very well. So the attendance is up to date. I think I'm a victim of copying and pasting because they are up to date. I said they're to be updated by the end of the week, but they are updated. I'll just put updated. Homework 5.1 is graded, and 5.2 is due today. 5.3 is assigned today, so we're sort of, you know, rocking and rolling. A couple things I do want to mention beyond my usual spiel for announcements. If you have a laptop, it would probably be a good idea to bring it next lecture, because what we're going to be doing is investigating the use of using Excel to plot shear and moment diagrams, because you're going to see the problem that we do on Wednesday. The graphical approach isn't really going to work. And plotting them out in Excel is going to be kind of nice. So bring laptops if you can for Wednesday. The other thing I do want to mention is the Career Expo. How many of you are planning on going? Good. So that's on Wednesday. It's from 3 to 6. It's over in the Student Center. If you have resumes, I would bring copies of those. How many of you are in 217 right now? Okay, so if you're in 217, you probably just got it ready. So you had to. So, but I think there's like 30-some companies that are looking for engineering students. I like money. I have a feeling you do too. So, summer gigs and whatnot, or maybe employment during the semester, that's the best place to find it. Make sure you dress somewhat professionally. I don't think you need to go, you know, full, you know, all out, but professional dress is required. Okay. All right, so today what we're going to do is we're going to continue our discussion of shear and moment diagrams, but as you probably have gathered with this class, you know, we sort of introduce a topic and then we day by day ramp it up a little bit. And so that's what we're doing today, is we're addressing shear and moment diagrams for uniformly distributed loads. So we're still using the same mathematical relationships that we derived in the previous couple of lectures. I would argue that today we're probably using those relationships a little bit more directly than we have in previous lectures. So just to make sure that we're clear, what we basically derived was a relationship between load, shear, and moment. And so what we found is that the change in shear is equal to the magnitude of the load, or flipping that around, if we want to find the shear, we integrate the load diagram, and then same way with shear and moment. The change in moment is equal to the shear, or if we want to find the moment, we integrate the shear. And so these are the conclusions for the graphical approach that we utilized in the last lecture, where we went from constant to linear, or constant shear diagram, linear moment diagram, etc. What I want to do today is I want to ramp it up, and I want to look at distributed loads. So remember, we use that integral relationship, and so now we're going to take that integral relationship and we're going to extend it 1 degree further. So if I have a constant load, okay, so I want to investigate this image a little bit because I think it's kind of important. Let me hit escape here because I kind of want to zoom in. I want to make sure that the notation is coming through pretty clearly. So let's first off look at the relationship between load and shear. So I have a constant shear, or constant load. So let's think about that from an integral perspective. So if I have the integral of 7, what is the integral of 7? It's 7x, right? If I have the integral of 93, it's 93x. The integral of a constant is a line. Now notice, I was very particular in how I constructed these schematics, because notice how I have a constant load, linear shear diagram, but notice how the slope is negative, okay? The slope is going down. The reason the slope is going down is because the load is going down. So mathematically, we would treat that as a negative load, so it is a negative slope, okay? So a negative slope on our shear diagram. And if we take that one step further, okay, so notice how we go from a region of what we'll call high shear to a region of low shear. What that means is that if we take a line and we integrate that, we get a parabola. So what our moment diagram will look like is something like this. So let's investigate this a little bit. Let me zoom out a little bit so I can capture the whole thing. So first off, we go from a line to a parabola because that's how our integral relationship works. If I take the integral of 2x plus 3, I get x squared plus 3x plus something. So going from a line goes to a parabola. Okay, let's look at the slopes. Okay, we have a high shear to a low shear. So we have a high slope to a low slope. Okay, so sometimes you'll hear me use the term lot to a little. A lot of slope to a little slope. It's because there's a high value of shears, there's a high value of slope on the moment diagram. We have a parabola. Notice how that parabola is sort of opening downwards. It's opening downwards because we have that negative slope on the shear diagram. So yeah, and as for the change in moment from point A to point B, that equals the area under the shear diagram. Again, just integrating. A lot of those patterns are again, very directly derived from what we've looked at before. And don't worry, we're gonna go through this with some pretty detailed examples here in a bit. Okay, so far so good? Now, what I have found when I teach this topic is that there is some geometry that we need to deal with. And I'd actually kind of want to look at this geometry off to the side because we're going to have this problem come up. This is actually going to come up in the problem we're about to do. And I want to make sure that we're not going to get tripped up on the little stuff and lose sight of the big picture. So I actually want to take this problem off to the side and just sort of investigate it, okay? So let's say that we have a shear diagram region that looks something like this. And this is all you know, okay? I need to determine the area under these regions, okay? And this is going to happen, right? You're drawing a shear diagram and you go from 25 kips to negative 75 kips, and now you need to determine the area of the shear diagram, and you're not going to know these distances here and here. So how do you do that? So I want to just make sure that's comfortable. This is not difficult. This is not very challenging, but I don't want to lose sight of just the construction of the shear moment diagrams while we have to figure this stuff out. So I'll show you a couple of simple ways of going about this. So first off, the first thing I'm going to do is see if I can compute the slope of this line right here. So we're talking about the slope of that diagonal line. And what I'm going to do is I'm going to treat this like it's a basic graphing problem, and we'll call it the change in y over the change in x. Why did I say change in y? Okay. So let's look at this from and let's also be a little diligent from our units perspective, because you'll see what happens here in a second. So change in y, maybe what we'll do is we'll take 25 kips minus negative 75 kips over 0 feet minus 25 feet. However you want to do it, if you want to be super diligent on the math perspective. So, you know, the coordinates of this point are going to be 0, 25. The coordinates of this point are going to be 25, negative 75. So however you want to do that. So we're going to get on the top, we're going to get 100 kips, and on the bottom, we're going to get negative 25 feet, or negative 4 kips per foot. Now, if it makes you feel better, this calculation, we don't even have to worry about that when we're actually doing a real problem. Why? Because the slope of the shear diagram is equal to the magnitude of the load. So I propose to you that wherever this region is on the, wherever this shear diagram region is on the beam, it's under the region that has a 4 kip per foot distributed load on it. So we don't even need to worry about that, okay? But in order to determine the area, let's say, of this triangle, what we're going to need is 1/2 base times height, okay? Now, I propose that the base is, quote unquote, the more challenging part to figure out. I know the height is 25 kips. I know that. That's not an issue, right? The height is 25 kips. But what is this dimension? What is this dimension here? We'll call it B. The easiest way to determine that distance is to use our fundamental expression here. If slope equals change in y over change in x, then the change in x is the change in y over the slope. So if you want a real simple way of determining B, just take 25 kips, divide it by 4 kips per foot. That's it. Does that make sense? So if we wanted this dimension here, we would take 75 over 4 kips per foot. So now this right here, so we'll call this equals 6.25 feet. So this is 1/2 6.25 feet times 25 kips equals what? I don't know what that is. I hear the familiar slides of the trays of Casio FX115 ES Plus or similar scientific calculators.
$78.125.
Foot kips. Do I have a second? Boom. So that's the area under the shear diagram right here. And if you want the area under this shear diagram, all you have to do is say, okay, this dimension right here is 75 over 4, which is, I don't know, 18.75. And so this area is 1/2 18.75 feet, 75 kips, whatever that is. Does that make sense? I don't want the geometry to trip you up with what we're about to do. I want that part to be simple. What is this, by the way?
703.125.
703.125. Do I have a second? Okay, so 703. Any questions?
Why can you not take the integral of the line and it work out?
Oh, you can if you want. That's fine. That works too.
So how would you do that?
Okay, so first off you would have to develop an equation for the line,
Right.
and integrate from this point to this point.
So you can.
All I'm saying is you're still having to do some math to figure out what these points are
You
anyway.
can't just do the integral from 0 to 25. It won't.
Well, what you're doing is getting the total area from here to here.
Right.
I mean, you can do that if you want. I'm saying I genuinely think this is a lot easier.
I did too. I was just curious.
Let me answer it this way. Give me a couple lectures and you will see we are going to have to take some integrals of some of these diagrams in order to compute deflections. Because what we're going to have to do is essentially multiply moment diagram times moment diagram. Remember how we had little f times big F? We're going to have little n times big N. And we're going to have to integrate those because the moments change. So what you're talking about, we're going to get there, but it's going to take us a little bit. ahead of the curve. All right. Any questions? All right. I want to spend the remainder of lecture on a problem. And I want to take what we've done so far and ramp it up a little bit. So I would like to look at this problem. Okay. Notice what I didn't give you on this problem. I didn't give you the support reactions. Because I'm a meanie. That's weak, isn't it? I'm doing that on purpose, though. I'm doing that on purpose for this problem because I want us to have an inherent understanding of what these reactions are and how they feed into the checks and balances on the moment diagram we're about to construct. So I think that for the purposes of learning this topic, for this problem, I think that, I'm sorry, we need to compute them, okay? So we are going to take our time and compute these shear diagram, or these reactions. Now I'm squunching my beam a little bit over here because what I'm going to do is I'm going to do my computations over here, and then I'm going to draw the diagrams over here. So hopefully I can squunch all that together. Now I want to do this problem the way I think you're going to do it on your homework assignment, okay? And how you're going to do it on exams. So I want to sort of fully embrace the potential errors that you're going to encounter and deal with them head on. I don't want to scooch them off to the side, okay? So let's handle this. Okay, so the first thing I think we need to do is we need to compute these support reactions. Now, whenever we were computing support reactions before, what would we do with the distributed load? We would collapse that into a single point load, right? Let's do that. I have 3 kips per foot, and it is over a distance of 60 feet. So I can collapse that into a single point load of how much? 180. And that's probably going to be somewhere about there. And how far from A is that going to be?
30 feet.
30 feet. If that's too small, or if there's anything that's illegible, let me know. I know there's I'm trying to, make it big enough to where you can see it. Okay, so what I'm going to do is I'm going to handle this like I would any problem. I'm going to sum moments at A. Actually, hold on. Let's note let's just be formal about it. Let's recognize that summing forces in the x direction. We know that AX is 0. Now let's sum moments about point A. All right. Okay. So we've got 180 times 30. 30 times 40, 60 times what? What's the moment arm for this point? From summing moments from A, what's the moment arm for this load right here? 80. Exactly right. And the only thing resisting that is going to be Cy times a moment arm of 60. Okay? So what do we got? We've got 5,400. I think I did that right. 1,200, 4,800, 11,400. I did that right? Yep. All right. So 11,400 divided by 60. Now what is that? I might need some help on that.
190.
190. So Cy is plus 190 or 190 kips going up. And so if I sum forces in the y direction, so I got 180 down, 30 down, 40 down, and I got AY up, CY is 190 up, so AY plus 190 is 180, 30, 40, bless you, 270. Did I do that right?
I think it should be 60. Yeah, 740.
Wait, what?
In your
You
table.
got
Last slide.
40 going down.
Huh? Oh, wait,
Where'd you get a 40 kips going down?
this one. Oh! I didn't know what you were talking about. I was like,
How many mistakes is that?
none, because we caught it. Again, it's a corrupt system. We'll add 0.125 to the sake of that. I don't know where we're at on the mistake count, but
It should be plus 100.
plus 100.
Because there's an extra 20 from the.
Well, hold on. So 180 down, 30 down, 60 down. 180, 30, and 60. So 30 and 60 is 90, 180, 270. That's 180, 80.
Oh, yeah, my bad. Yeah.
Is it right?
Yeah.
I'm hearing second, so we're going with it. We'll find out if it's wrong here in a second. We'll actually find out. Okay. Let's get everybody a sec to catch up, and then we'll move on. Let me, though, while everybody's catching up, let's draw some guidelines here. And so normally what I like to do is when I'm drawing these things, at a minimum, I like to draw them under all the letters, because if they were important enough to be named, they're important enough to be considered in my analysis. See, that's the beauty of shear moment diagrams. If something's wrong, I'll find out. I'll find out. Okay. All right. All right. While we're at this, let me also just do this. Let me say CY is 190. Why don't I ever use like the galaxy pen? Spice up calculations a little bit. Okay. All right, so AY is 80, CY is 190. I think we're ready to start constructing a diagram. Okay. All right, now, so what do? We strike a horizontal line. I'll put my label over here. Okay. We start out with 0. Let me put all the tick marks on here. Let's see what I end up at. Okay. Everybody caught up with me? Okay. So the first thing that we do is what? Tell me what the first thing we do is. Up 80. So we're up 80. That puts us probably somewhere about like that. Let's just pick a point for scale. We'll say that's 80. Now, before we draw anything, I want all eyes up here. Because it is very easy during these problems to go like this, down 180. It is very easy to do that. If you find yourself doing that, take your hand and do that, because that's wrong, okay? Remember, what is this 180 kips? Was that originally on the beam? Absolutely not. We put that there just to make the summation of moments for the computation of our support reactions a little easier. But from here on out, we ignore that. That does not exist. Gone. Okay? So in fact, if you want, or if you're okay with this, I'm going to erase this. This doesn't exist. Boom. That is not there. Okay? So, let's see what is there. What is there? Tell me what's going on from point A to point B. First off, let's answer some simple questions. Am I going to be going up or down?
Down.
Down. Okay? Now, am I going to be going down in a constant fashion or a linear fashion? Well, the last few slides tell me that if I have a constant load, it should be linear, right? Just so we're paying attention, what is the slope of that line? -3. Now, how far from A to B? 40 feet. So, how much load is that in this 40-foot region? 40 feet, 3 kips per foot. How much load is that? 120?
Yeah.
So if I'm at 80 and I drop down 120, that puts me down about right there at what? -40. So the shear diagram should look like that. -40. Well, by golly gosh gee, it's like that geometry problem I mentioned a second ago where we're going to have to integrate. I didn't want that to be a problem, so that's why we did it off to the side. All right? Now I'm at -40. What do I do?
Down another 30.
Down another 30 to put me at -70. Now I'm at -70. What do I do from B to C? Keep. Exactly. So if I'm at -70, how much do I drop from B to C? Is a magnitude of 60 or -60? Because it's 3 kips per foot over a distance of 20 feet. So if I'm at -70, I drop down another 60. That puts me at 130 or -130. So -130. Then what happens here? Whoo, massive jump upwards, right? Because we got huge reaction there at C, 190 kips. So if I'm at -130 and I jump up 190, that puts me at what? Positive 60. So that's probably going to be about like that. Then what does the shear diagram look like from C to D? Flat, straight line, 0 load, 0 slope on the shear diagram. 60, then oh my golly gosh gee, look at that, drop back down to 0. There's your shear diagram. Starting to ramp it up a little bit from Engineering 213 already, but in the end, hopefully this isn't that challenging. I mean, we're just taking the same patterns and just extending them. Okay? All right. Everybody with me so far? Now, conceptually, in order to construct the moment diagram, what do I need to do? I need to integrate this, compute the areas. I'm going to work backwards. And I'm going to work backwards because I think it's easier, like, to go this way. So, what is the area under this first rectangular region right here? What is the area? 60 times 12, or 60 times 20, sorry, 1,200. That's exactly right. All right? Now, all right, let's look at this region. I'm going to show you a little shortcut, okay? All right? I could take this region right here and handle it 2 different ways. One way is to split it up into a rectangle and a triangle and compute each separately. Here's another way of handling it. Let me scroll down a little bit. I'll say note. There's a name in geometry for that shape. We call that a trapezoid. And the area of a trapezoid can be found by by taking the base times the average of the heights. Because essentially what you're doing is you're saying, I'm going to knock off that little triangle right there, and I'm going to stick it right there. And so then it just becomes a rectangle. And how do you find that height? You just average this and this. So that little bit goes over there. So if I want to find the area of this region right here, what is the average of 70 and 130? 100. How wide is it? 20. This is negative 2,000. Does that make sense? So that's a little shortcut there for you. Now, the real work is going to become, or is going to happen in this next component. So, first thing I'm going to do, I'm going to draw myself a little guideline going down, because I can tell you, any time that the shear diagram crosses 0, that's going to be important later. Now, how do I know that? I seem to remember from Calc 1 that the first derivative seems to be a way of identifying the extrema of a function, right? In other words, if the shear is 0, that's going to be a local minimum and maximum for our moment diagram. Let's see how that works out. Before, we got to deal with our shear diagram first. We got to get some areas, okay? So help me out. Let's get this distance and this distance. Now remind me, what is the slope of that line again? -3 kips per foot. So how do I determine this distance easily?
80 divided by 3.
80 divided by 3, and what is that? It's not pretty, it's like 26.67. I think, did I do that right? So this, 26.67 feet. That's the width of that line. What about this line over here? What's the width of that? What about this line right here? How do I find that? So it's 40 over 3. And 40 over 3, I think, is like 13 1/3, 13.33 feet. So this that's the width of that line right there. Now we got to determine areas. Now remember, here's another thing, and I'll just level with you. One of the most common mistakes I'll find is that when determining the areas, you forget to divide by 2. It's a triangle. Base times height over 2. So don't forget the 2. So what's the area of this triangle right here, this first one? So 80 times 26.67 over 2. It's not a pretty number.
1066.8.
1066.8. Okay, now let's talk about that. That's totally fine. Okay, I want to be clear on that. That's totally fine. If you carry out your decimals, it ends up being 67. The reason that you got 0.8 is because you literally just typed in 26.67 instead of like 26 2/3. That is completely fine. I have no problem with that in any way, shape, or form. What I want you to know, though, is that if you're a little liberal with your rounding, what can happen is that you can start at 0 and end at like 0.3 instead of 0. That's fine. I don't have a problem with that. Just know that if you're on a homework or on an exam and it doesn't quite end back at 0, that's probably why. Okay? Is everybody okay with that? So just make sure that you're aware of that. Now, the area of this region right here, what's the area of that? And it's going to be negative. 40 times 13.33 over 2.
Negative 266.6.
Okay, there we go. All right. Now we are done with our shear diagram. All right. Does that make sense? Okay. If I sum up the areas, what do I get? Okay, so I get this plus that, which is what, 800? 800 plus this, which is negative 1200. 1200 plus this, 0. So we're doing something right because some of the areas are 0. All right? So now let's construct our moment diagram. All right, let me scroll down a little bit so I'm not squunched down at the bottom of the screen. And I want to wait for everybody to catch up with me on this because I want to show you a simple way of getting this right. Okay. I still see some folks drawing this stuff out, so this is totally fine. Take your time. All right. Now, help me out. So the new stuff with today, the new stuff is just the shape of the moment diagram. We can handle the construction in actually the same way we did before, so the shape is a little different. Let me explain what I mean by that. So let's start off indicating 0 right here at the bottom. And let's see what happens from region to region solely from a rises and falls standpoint. In other words, from here to here, I'm going to start at 0 and I'm going up 1066.67. Okay? Okay, I don't know yet, or I know, but we haven't yet plotted it out. But would you agree from here to here, that's how much we're going to go up? Okay, from here to here, if I'm at 1066.67 and I drop down this much, what does that put me at? 800. So this is probably going to be 800. Now what about, here let's add some guidelines. Starting to see why I said straight edges might help on homeworks and exams. Just start doing stuff like this for a while. All right, so here's the moment, here 800, so I'm at 800, I drop down 2,000. What does that put me at? Negative 1,200. So we got a sharp decrease to about right there. And then this is going to bring me back up to 0. So regardless of what I draw, okay, I better reach these peaks and valleys along the moment diagram, because we know that's true. Okay. Now, okay, that's point 1. Point 2, what's the easiest region to figure out on the shear diagram? I would argue it's this region over here, right? Constant shear, linear moment. I know this is going to be a straight line. That's a straight line. Easy. What about everything else? Okay. All right. This is something I mentioned earlier, so I want you everybody to pay attention up here. Okay? Talking about that integral relationship. Okay? I want to look from here to here, from A to this point. Notice how we have a lot of shear, and notice how we have, what's the shear value right here? How much shear is in the beam? 0, right? Make sense? What does a line look like with 0 slope? It's flat. So the line better be, the curve better have zero slope right here. Okay? What about over here at the very end? What's the value on the shear diagram? 80. What does a line with a slope of 80 look like? Steep, like that, right? So, what's happening is that as we go along this way, we have a slope, a slope, a slope, a slope, a slope, a slope. And so the curve should look like this. Like that. And so in statics, you probably heard me say a lot to a little. A lot of shear to a little shear. A lot of slope to a little slope. So what about this region? This region, it just continues, okay? Like that. In fact, my artwork is absolutely horrible. But from here to here, it's actually the same parabola. It's the same parabola because it's the same line of shear diagram from here to here. We're actually going to talk a lot later about how many mathematical functions are required to fully define a moment diagram. That's going to be a topic of discussion that's coming very quickly. Okay? Now, let's talk about this region. Okay? Because I've already peeked at a couple students, and I think there might be a couple of tweaks that need to happen. What is the slope got to be right here? Negative 70. What's negative 70 look like? Maybe about like that? Okay. What does a line with a slope of negative 130 look like? Like, whew, that's sharp, right? So the moment diagram in this region, and my artwork's horrible, forgive me, should look like that. So a sharper parabola. So if you want, maybe what I'll do is I'll say linear, quadratic, quadratic. Does that make sense? I know my artwork, I know this looks an awful lot like a line. I'm sorry. I'm not an artist. So this tells me as a designer, I need to select a beam that can withstand a maximum positive bending moment of 1066.67 foot kips and a maximum negative bending moment of negative 1200 foot kips. So maybe what I'm finding is different configurations of the beam from one end to the other. We see that in bridges, reinforced concrete, and steel design all the time. I also see one hell of a jump in the shear diagram right here, so maybe I need to throw in some extra web stiffeners or shear stirrups in the beam right here around this support because we've got a heck of a concentrated force right there. Let's take it in. Let's absorb it. What are we thinking? Any questions? Yes?
Why was there no consideration for the 70 kip, negative 70 kip
Negative 70 kips where?
on the shear diagram?
What do you mean, right here?
Yeah.
Okay, so there was, and my artwork is horrible. I'll show you why. So let me do my best. That's a really good question. So what's happening right here is there's two parabolas, okay? And I'm going to do my absolute best to try and draw this out. So what's happening is, so there's a parabola over here that's sort of stopping like that, right? Okay, and this parabola at that point right there has a slope of negative 40. Then what's happening is there's a new parabola that's sort of starting like that, and it's got a slope of -70. That's a really good question. Yeah. My art is just absolutely horrendous. Yeah, that's a really good question. So, and let me answer that with another added sort of addendum to that. This is the type of thing that is going to be easier to understand and see if we plot with software. Because the software is going to be able to handle that. It's going to take our artistic skills and they're not going to matter. That's a really good question. All right. Any questions? All right. Laptops on Wednesday if you can, because we're going to use some Excel to construct some shear moment diagrams. We're going to find a spot where this graphical method breaks down. That's all I got. I will see you all on Wednesday. Don't forget the career fair as well.